My name is Michael Kokenderfer, and I'll be discussing our work on validation of decision-making systems for safety-critical applications. I'll begin by discussing our work on a validation method that is sampling-based, which can scale to complex problems but does not provide formal guarantees. Then I'll discuss some work that we have been doing on formal methods for verifying properties of neural network controllers. Finally, I'll show that these methods can be combined to discover interesting failure cases involving a neural network controller for taxiing an aircraft. One of the key tasks in validating a complex decision-making system is to identify the most likely failure. This is an optimization problem where we try to maximize the probability of a trajectory subject to failure. The key insight here is that this is an optimization problem that can be framed as a reinforcement learning problem. We call this process adaptive stress testing. And here we have a simulator that encompasses the environment, a model of the environment, and a system under test. That system under test could be something like an aircraft collision avoidance system. We only need to be able to execute that system under test. We treat it as a black box. We don't need to peer inside of the implementation at all. The simulator outputs an observation and a reward. We want the reward to be related to the log probability of the transition in our environment according to some model. Then we have a reinforcement learner that tries to optimize with respect to that reward. And in reinforcement learning, we try to maximize the expected sum of rewards. And so if we're maximizing the expected sum of log probabilities, we're actually maximizing the likelihood of that trajectory. We can use different kinds of reinforcement learners, such as Monte Carlo tree search or deep reinforcement learning. These reinforcement learners output actions, and these actions dictate how to perturb the various environmental variables. The output of this adaptive stress testing process is the most likely failure path, starting from some initial state or state distribution to some kind of failure state. We released an implementation of this on GitHub. The really cool thing about adaptive stress testing is you get as output a simulation trace that the engineer or analyst can then step through and try to analyze and understand what's going on and maybe suggest some mitigations. So what you see here is a plot of the lateral positions over time for two aircraft with the ACAS-X system, and on the right the vertical profile indicating the various resolution advisories that are produced over time. And this was extremely important information during the development of ACAS-X leading up to the standardization. With the success of the application of adaptive stress testing to collision avoidance, my students were very interested in seeing how it would apply to the automotive setting. What you can see here is a simulation in the Carla simulator. It's an open source simulator. We're simulating a controller on the car that is fed by a perceptual system. You can see the bounding box around the pedestrian here. What we want to do is find the most likely failure with respect to a model of the dynamics and the sensor error characteristics. What we can see here is that the most likely failure is actually not very interesting. It's not relevant because we're clearly not at fault. The pedestrian is running straight at the car and flinging themselves at us. So we changed the reward function slightly so that it would focus on situations where our system is at fault, according to the RSS system produced by Mobileye. What you can see here is that the bounding box is bouncing around and maybe your car is driving a little bit aggressively. Understanding this failure at design time is very important because it might suggest changes to our sensor system. Maybe we add an additional sensor to the system, or maybe we tune some of the parameters in the Kalman filter, or maybe we tune down the aggressiveness of the car. So adaptive stress testing is sampling based, and so it doesn't provide any formal guarantees about the safety of the system. We've also been exploring methods that do provide these guarantees. So it started out with some work that we were doing on trying to represent a tabular policy for an aircraft collision avoidance system. This system you can find on GitHub. It's a notional system, just a toy that we can play with, but the idea is to compress this table policy that's represented by 1.22 gigabytes of information. And we found that we can compress it very nicely using a neural network that occupies only 103 kilobytes. As you can see, it's not perfect. But it turns out that when we run it in simulation, it performs actually quite well. So that led us to think about ways that we might be able to provide validation of this system in a formal way. That work on neural network representations of collision avoidance that led to the creation of the Rayleigh-Plex algorithm in collaboration with Clark Barrett's lab. The Rayleigh-Plex algorithm was published in 2017, and in that year and the years following, a number of other algorithms have been developed around the world. My former postdoc, Chonglu Liu, who's now a professor at Carnegie Mellon University, she went through and re-implemented a number of these algorithms in Julia, and we produced a survey, about 80-page survey of these different algorithms, and the implementation is available on GitHub. So we can use these neural verification tools to prove properties about the neural network, and it involves reasoning about the weights in the neural network, so we can actually arrive at a proof over the full continuum of inputs and their relationship to the outputs. So we can use this for reachability analysis. In this work done by Kyle Julian, what we did was discretize the state space, and for now we'll just focus on the one cell that's outlined here in red. We can call out to one of these neural verification algorithms and prove that within that cell only two different advisories are available, so either a descend 1500 or a climb 1500. And we can use an over approximation of the dynamics to say that if we do apply a descend 1500 from that cell, then we will end up in only those two cells. And similarly, if we issue a climb 1500, then we only end up in those cells. And we can reason about the cells that we end up in from those cells. We've applied this technique to study reachability for both vertical avoidance maneuvers as well as horizontal avoidance maneuvers. This is an example of a horizontal avoidance maneuver. What we want to show is that the intruder aircraft cannot come within a certain threshold of us if we follow our advisories. I'd like to briefly highlight some of the work that my student Kyle did on TaxiNet. So TaxiNet is a neural network that has been trained to follow the center line of a runway or a taxiway. And what we want to do is figure out whether image errors can make the aircraft depart the runway or the taxiway. This is done in the X-plane simulator, which is a photorealistic aircraft simulator. The camera is mounted on the side of the aircraft, and we want to translate those images into steering commands. So we take as input the image, we downsample it. That image, the downsampled image, is then passed into the neural network. The neural network outputs predictions of cross-track error as well as heading error. And then from those two quantities, those are fed into a simple linear controller that outputs rudder or nose wheel commands. And this then gets updated in the simulator. So before we started using our neural network verification tools, we started playing with different lighting conditions, ranging from clear days to overcast days. And what we saw was that the neural networks actually seem to perform extremely well. So we used a series of calls out to Marabou to try to get it off the left side of the runway, just by finding the perturbation that leads to the most extreme rudder command. And you can see that we actually succeed a bit here. We get it off to the left a little bit, but then no amount of allowed perturbation prevents it from correcting itself, and we are not actually able to get it off the left side of the runway. So we combined adaptive stress testing with calls out to Marabou, and we varied the amount of allowed perturbation. If the perturbation is limited to 2%, then the system we find is actually quite safe. However, if we increase the allowed perturbation to 3%, then adaptive stress testing finds a very interesting failure where it leads it off to the left side of the runway, and then it produces steering commands that have it go over to the right side of the runway. Now, the neural network finds itself in a situation that's very different from the data on which it was trained, and it doesn't know how to recover from that situation. If we increase the allowed perturbation to 3.5%, it actually goes over to the right and then is able to get it to fail a bit more quickly. It figures out to go in between the dashed line of the runway because you can get away with less perturbation and fool the neural network. And then if you bump it up to 4%, it's actually pretty easy to get the aircraft off the side of the runway with just extreme steering commands. So we can add additional actions to adaptive stress testing to allow for lower perturbations. And what we find is that we can get extremely interesting situations where we can actually cause failures with not very much perturbation. As we saw with aircraft collision avoidance and automated driving, finding the most likely failure in a dynamic system can be framed as a reinforcement learning problem. There are no formal guarantees, but it has been successful in finding failures that are very useful during the design phase of a decision-making system. To provide formal guarantees, we can combine neural verification algorithms like ReLUplex with over-approximation of the dynamics. For problems where the input to the system is an image, we have been able to combine formal methods with adaptive stress testing to find interesting failure cases that would not have been found using sampling-based or formal methods on their own. I'm very excited about the hybridization of these approaches, and we'll have to see how far we can take them. These are still very early days. You can find my email at the bottom of the slide, as well as a link to the webpage of the Stanford Intelligent Systems Laboratory.